In this video, we will solve a problem related to Exergy destruction. The problem states as follows. Figure shows a turbine operating at steady state with steam entering at P1 equals 30 bars, T1 equals 350 degrees Celsius and a mass flow rate of 30 kilograms per second. Process steam is extracted at P2 equals 5 bars, T2 equals 200 degrees Celsius. The remaining steam exits at P3 equals 0.15 bars, X3 equals 90%, and a mass flow rate of 25 kilograms per second. Stray heat transfer and the effects of motion and gravity are negligible. Let T0 equals 25 degrees Celsius, P0 equals 1 bar. The accompanying table provides property data at key states. For the turbine, determine the power developed and rate of exergy destruction, each in MW. Also devise and evaluate an exergetic efficiency for the turbine. Once we have read the problem, we have the following data. For inlet number 1, we have a temperature of 350 degrees Celsius, a pressure of 30 bars, and a mass flow rate of 30 kilograms per second. For outlet number 2, we have a temperature of 200 degrees Celsius, a pressure of 5 bars. For outlet number 3, we have a pressure of 0.15 bars with a quality of 90% and a mass flow rate of 25 kilograms per second. First, we perform a mass balance. Thus, we have that in the control volume, which is the turbine, the mass flow 1 must be equal to the mass flow 2 plus the mass flow 3. From the previous expression, we solve for mass flow 2, since it is a piece of data that we do not have. Thus, mass flow 2 is equal to mass flow 1 minus mass flow 3. Substituting, we then have that mass flow 2 is equal to 5 kilograms per second. Then, to determine the power developed by the turbine, we have to do an energy balance for a control volume. The energy balance is as follows. 0 is equal to the heat transfer inputs or outputs minus the power developed by the control volume plus the sum of mass flows by inlet enthalpies minus the exit of mass flows by outlet enthalpies. Afterwards, we solve for the power to be developed by the control volume. Thus, we have that the mass flow times enthalpy number 1 minus mass flow number 2 times enthalpy number 2 minus mass flow number 3 times enthalpy number 3 will be equal to the power developed by the turbine. Substituting, we then have that the power developed is equal to 30 kilograms per second times 3115.3 kilojoules per kilogram minus 5 kilograms per second times 2855.4 kilojoules per kilogram minus 25 asterisk 2361.7 kilojoules per kilogram. Performing the operations, the result is that the power developed by the turbine is 20.1395 megawatts. To know the destruction of energy, we make use of the expression for steady state of a control volume to know the reason for an entropy balance. Thus, then using that expression with the data we have the following. 0 is equal to the heat input or output plus the mass flow inputs multiplied by the inlet entropies minus the mass flow outputs times the exit entropies plus an entropy generation factor of the control volume. Since there are no heat losses, to determine the production entropy, the expression is as follows. Mass flow 2 by entropy 2 plus mass flow 3 by entropy 3 minus mass flow 1 by entropy 1. Substituting data, we have the following results. The entropy production is equal to 15.0895 kilograms K. Then, to know the destruction energy, the expression is ambient temperature times the entropy production in the control volume. Thus, substituting, we have that the exergy of destruction in the control volume, which is a turbine, is 4.4966 megawatts. As an additional exercise, you can develop an expression for exergetic efficiency if you want to see how an expression for efficiency looks. Let me know your comment. Explanation of the solution.